The question that I have is, could you do an example involving triaxial CU test data? In this example, an undrained triaxial compression test was performed on a saturated sample of normally consolidated clay. The consolidation pressure was 100 kilopascal. The specimen failed when the principal stress difference was 85 kilopascal and the induced pressure, pore water pressure, was 67 kilopascal. A companion undrained test was performed on an identical sample of the same clay but at a consolidation pressure of 250 kilopascal. The questions are: number one, find the maximum principal stress difference you would expect for the second specimen, and what are the values of phi prime and phi total for this clay. Let's take the first part. You can do this in two different ways. I'll call these as method 1 and method 2. Method 1, you work in the PQ space. We recognize that the undrained effective stress pads conducted from different confining pressures are similar, geometrically similar. Another way of saying that is triangles OAC and OBD are geometrically similar. Then, using the principle of similar triangles, we can write down this equation right here. Q2F divided by Q1F must be equal to 250 divided by 100. So that gives you, in a straightforward manner, the principal stress difference in test 2 to be 212.5 kilopascal. The second method hinges on the recognition that phi prime and phi total are constants. Doesn't matter whether you take failure stresses from test number 1 or test number 2, we should arrive at the same values. These are undrained tests. At this point, we don't know the pore water pressure at failure. So let's work with total stresses. So that means I'm going to set the total friction angle to be the same for test number 1 and test number 2. So I take the results of test number 1. Sigma 3F is 100 kilopascal. Sigma 1F will be 100 plus the deviatoric stress at failure, which is 85 kilopascal. Therefore, sigma 1F is 185 kilopascal. We also recognize that we are working with a normally consolidated clay specimen. Therefore, CT must be equal to 0. And then we come back and apply this equation right here and substitute the numbers we know, which are sigma 3F is 100 kilopascal, sigma 1F is 185, and that gives me a total friction angle of 17.35 degrees. Now we take specimen number 2, for which sigma 3F is 250 kilopascal. So we reapply this equation. Now this time we know the friction angle, and the only unknown in that equation is sigma 1F. So sigma 1F works out to be 462.4 kilopascal. Now we find the difference between the two. We find the principal stress difference of 212.4 kilopascal, which is same as this. Now you may want to note that regardless of whether I use the difference in the effective principal stresses like I did over here, or the total principal stresses, it should be the same because the pore pressure cancels out. So we are done with part A, but as part of that we also found the total friction angle, which is part of the question of part B. So what remains to be done is to find phi prime. I can either work with test number 1 or test number 2. So let's take the result from test number 1. We have the total stresses here. Pore pressure is 67 kilopascal. So we subtract the pore pressure from each of the total stress components and we get the effective stresses at failure, which are 118 kilopascal and 33 kilopascal. And we come back and reapply this equation in order to get phi prime. So phi prime works out to be 34.25 degrees.